I'm very happy to introduce Ben Pearce, who's a PhD student of Nikitas, Gidopoulos, Durham University. And Ben and I overlapped a little bit during the end of my PhD and the start of his. And we did some work together on various techniques to solve the optimized effective potential equation and applications of that. And Ben will talk about some of those today. For example, whether spin DFT and normal DFT share a common limit in the absence of a magnetic field, and also some stuff he's done since I left on Ensemble DFT and the derivatives discontinuity. So yeah, I'll hand over to Ben now.
Thanks very much, Tim. Thanks again, Tim, for the nice introduction, and thank you to the organisers for arranging this event. So I'm going to be talking to you today about exchange correlation density functionals with spin density accuracy for open shell systems. So what's the motivation behind this talk? Well, from Parr and Yang's famous textbook, they state that the approximate form of a spin density functional can be, and usually is, a better description of a real system than the corresponding exchange correlation density functional. It's surely the case for spin polarized systems such as open shell atoms and molecules. So the idea in this talk is to revisit this common wisdom within density functional theory and develop an OEP equation, or an optimized effective potential equation, to construct new density functionals with spin density accuracy for open shell systems with the same computational cost as the underlying spin density functional approximation that you're using. So the first part of my talk is going to be about the optimized effective potential, for those aren't too familiar, and how we can actually reliably and efficiently solve this equation. So if you have a functional which depends implicitly on the electronic density and explicitly on the cone-sham orbitals and their energies, you can use the optimized effective potential to calculate the exchange correlation potential. This could also be the Hartree exchange correlation potential. It depends what functional you might be using. By utilizing the chain, the functional chain rule, we can re-express this in the following way and recognize on the far right-hand side the inverse of the so-called cone-sham density response function, which is shown on the slide below. So the response function is the sum over the occupied and the unoccupied cone-sham orbitals within the slated determinant. By inverting this equation, you can then get the famous OEP equation. This equation has been around for a long time. However, in finite basis set applications, trying to solve this equation leads to potentially extremely severe numerical issues and really ugly oscillations, and yields some pretty pathetic exchange correlation potentials. So a common way to get around these problems is to use an approximation such as the CEDA approximation, where we use the unsolved approximation and take the difference between the unoccupied and the occupied orbitals as being a constant delta. And this allows us to re-express the OEP equation the following way. And the CEDA approximation works pretty well in finite basis set applications for local and semi-local functionals, but it falls short when you're looking at something like exact exchange. The main benefit of using something like CEDA is it's actually free from these numerical instabilities that are present within finite basis set solutions of the OEP equation. So how can we actually go about implementing the OEP equation in a sort of naive way? Well, we can expand our orbitals in a finite basis set, and we can express the effective potential in the following way. Following the work from Andy Girling and his collaborators, we express the effective potential in the following form in terms of a screening density, which can then be expanded using an auxiliary basis set, which takes the following form. So this allows us to then re-express the OEP equation as a matrix equation and search for solutions to the coefficients rho ks. It's important to note that we're not searching for the coefficients of the potential. When we're solving this matrix equation, we're trying to actually construct the screening density, which we can then reconstruct the actual exchange correlation or effective potential from. Important feature with the OEP equation and its solution is that actually the potential and screening density is only determined up to a constant. So that means that we need to impose some kind of constraint on our screening density. And we do so by setting the integral of the screening density to a value Q screening. And you can think of this screening density as the kind of mean field that's felt by each electron in the system. So that kind of sort of gives us a hint as to maybe what physically this value Q screening should integrate to. Because we know that electrons aren't supposed to interact with themselves, it'd be fairly obvious then to set this value Q screening to be the number of electrons in the system -1. This would then correct for self-interaction errors, and also it corrects the asymptotic behavior of the potential. This is an exact condition, but for approximate functionals such as LDA or PBE, this value actually wants to naturally integrate to n, and that obviously leads to a lot of self-interaction problems in your potential. Another condition that we imposed on the screening density was a particular positivity constraint. This avoids shifting negative screening densities out to infinity as your auxiliary basis set size increases for an approximate functional. So why might the screening density want to actually be pushed out to infinity? Well, if you imagine doing a calculation for LDA that naturally wants to integrate the screening charge to n, and you're forcing this extra hole to be present, if you give it the flexibility in the basis set, it will naturally want to move that hole away from your system, which doesn't really lead to very physical behavior. We did quite a lot of work amongst the group sort of investigating this condition. And we found that although it works, it's quite strong and it's not necessary, provided you use a small enough auxiliary basis set and you have enough electrons in your system. So I mentioned these numerical problems with the OEP equation. And as I said, these usually manifest themselves as some pretty strong spurious oscillations in the potential. But over the years, many methods have been developed to combat these difficulties. In this work, we use a particular method developed by Nikitas and Nektarios, whereby they denote a complement to the response function, and adding on a small complement term can then combat these numerical issues. As I mentioned before, the OEP solution is valid up to a constant, and it's important to note that the complete response function in an infinite basis limit is actually invertible. So you shouldn't, if you have the complete response function, you shouldn't encounter any invertibility problems. But obviously within a finite basis set, we don't have all the information about the response function. So what is this complement and how does that work? Well, the idea here is to split the response function into two separate terms. For simplicity here, we're assuming that up to the number of orbital basis functions is the Kohn-Sham orbitals plus a subset of the unoccupied orbitals. In the remaining terms, above the number of orbital basis functions up to infinity, we denote this term as the complement to the response function. So therefore, in practice, we can represent the full response function by the matrix elements AKL, which is the sum of these two parts. And we can undergo a very similar process for the right-hand side function B of R. So by including complement terms with alpha much less than 1, so near 0 but non-zero, we can then alleviate the issues with the full OEP solution of finite basis set. Alternatively, you could neglect this complement, and that's what Andy Gerling and his group would do, which is essentially use a larger orbital basis set for a given auxiliary to capture more information about chi0. And this has advantages. However, if you've got a big system and you're increasing your basis set size, that's going to really slow down and hinder your computational efficiency. So just as an example to show how these kind of two approaches work, here I've plotted the results of the exchange correlation potential for the neon atom using LDA-OEP. You might ask, why on earth would I want to do LDA with OEP? Well, it's because we're trying to enforce this n-1 constraint on the screening charge. So if you look at the left-hand figure, you can see three curves. So in the blue, we're showing there's no complement term here, and we're simply showing the result for the exchange correlation potential for a double zeta orbital basis and a triple zeta uncontracted auxiliary basis. You can see that the potential here is completely crazy, not very desirable at all, and is not the correct result for the system. But you can see if I increase the orbital basis up to a triple zeta, I now actually get a very nice potential. However, by increasing the basis set, it's incurring more computational cost. Alternatively, you can see that the green dotted, the dashed dotted green curve is for adding a small complement term of alpha is 0.01 and still using a smaller orbital basis of double zeta. The results for these two are actually very close together. The difference is obviously being the basis set is slightly different. You can clearly see that we are actually achieving the same OEP solution here. So for a neon, this isn't so, it's not so striking. But again, if you're looking at something, a much bigger system where you've got multiple numbers of electrons and a lot of basis functions, this computational improvement using a complement can be quite significant. So that kind of finishes the sort of OEP intro, just to show that how we can solve the OEP solution reliably and efficiently. And I kind of now want to move on to the sort of main focus of the talk, really, and that is, what is the problem with the current density functionals for open shell systems? So recall from the motivation slide, the quote from Parr and Yang. So what they're saying here is that for an open shell system, you really need your density functional to be spin dependent. So if we think about any common local or semi-local DFT functional, what we're doing is we're modeling that on the spin unpolarized electron gas. So say if I take beryllium atom, which has say got 4 electrons, the uniform unpolarized electron gas will simply say we've got 2 up, 2 down electrons, and that then is will calculate the exchange correlation potential. For say lithium, however, where we've got 3 electrons, it's slightly different, because we're now going to end up with 1.5 spin up and 1.5 spin down. And clearly this is going to lead to some very unphysical exchange interactions. So we can't use a spin unpolarized electron gas model for an open shell system. We need to come up with something a little bit more clever. So obviously the simple solution would be to use spin DFT, but what we're trying to do here is stay within the realms of DFT, but obtain an improvement in the accuracy for this open shell result. So we asked ourselves, can we construct approximate density functionals that have this improved accuracy of spin DFT? And we came up with the idea of implicit density functionals, where we construct the functionals such that the spin densities are themselves a functional of the total unpolarized electron density. And this leads the total energy functional system to be written in the following way. Again, we can construct the exchange correlation potentials by taking the functional derivative of this now implicit density functional approximation energy for with respect to now the total density. So we can then construct an OEP equation for these implicit density functionals, which looks very similar to the regular OEP equation with a few tweaks. So if we start looking at the left-hand side, you can see that the total response function Callow system is now given as the sum of each of the spin subset response functions, which are each given by the following formula here. On the right-hand side, we've now got 2 terms, so we're adding together the individual spin channel response functions acting on the actual spin density. It's important to note that although the spin densities actually enter the OEP equation here, we are seeking a common local potential. So we are still within the realms of DFT and not spin DFT, despite this kind of looking a little bit deceiving, perhaps. So in order to implement these density functionals, we modified the Gaussian basis set code HIPPO, which was originally developed by Nektarios and his group over in Athens, and that's been modified extensively by the group that I'm a part of over in Durham. In order to run calculations in HIPPO, you require 1 and 2 electron integrals for the Cartesian and Gaussian basis set elements, which we use the games code to obtain these. And for comparison, for result comparisons, we also use games for spin DFT total energies, as these aren't available within Hippo. For further comparisons, we also use the Sci4 quantum chemistry package in order to obtain couple cluster energies. So I'm now going to show you some results for an implicit LDA calculations on 3 different systems, just to show how the OEP results converge nicely, and we are reliably solving the equation. So on the left-hand side, you can see the results for a doublet lithium atom, where the difference between the number of up and down electrons is 1. In the center, we can see the results for the O2 diatomic. This is a triplet state. And on the right-hand side, we can see the results for the quadruplet OH radical. So these results are all for a fixed, uncontracted double zeta auxiliary basis. And you can see that we're increasing the orbital basis to check for convergence here. I think it's fairly obvious that for the first 2 systems, we're pretty much converged even at double zeta. We don't necessarily need to venture up to higher orbital bases, but clearly for the OH radical, we do need to jump at least up to triple zeta. Despite this, you can see some convergence issues around the region around the atom, but the overall potential is very nice. So in addition, we can also look at total energy results. So if you think about the unphysical exchange interaction between fractional spin electrons that you would get from an unpolarized LDA calculation, that's going to have quite a negative impact on the total energy. So what we did was compare the unpolarized LDA energies with our implicit LDA energies against that of a local spin density calculation for the total energy for a variety of doublet and triplet state atoms and molecules. So if you scan the average percentage difference column row, sorry, at the bottom, you can see that for an unpolarized LDA calculation, we get a percentage difference around about 0.1%. Compare that to an implicit LDA, we're down to 0.001%. So these energies are far, far closer to the spin LDA results. I should say that for the molecules, these are all at equilibrium geometries. So moving on then, I'm going to show you a couple of dissociation curves for two different molecules and 2 different functional approximations. So to start off, we're looking here at the H2 molecule within the implicit LDA, or the LDA functional. And you can see on the left-hand side, we're plotting the dissociation energy curves for a unpolarized LDA calculation, a spin LDA calculation, comparing that against the benchmark couple cluster calculation, and then also superimposing our implicit LDA result. Now, you can clearly see here that if we look at the LDA result, you can see that the dissociation limit is incorrect, whereas the spin LDA approximation actually reproduces the correct dissociation limit for an H2 molecule. What's interesting here is that our implicit LDA also, for the majority of the dissociation curve, follows alongside the couple cluster, or sorry, the spin LDA result. It deviates slightly, and then around about 4 Bohr, it has a sharp kink in the curve, and then tends towards the asymptotic limit of the spin LDA result. What's actually happening behind the scenes here is for the implicit LDA, this point corresponds to where the singlet state becomes higher in energy than the triplet state. Whereas with LDA, this actually never happens. If you run 2 simple unpolarized LDA calculations, the singlet state will always remain the lowest in energy. The triplet state will never ever cross. And that's what leads to this incorrect tail in the dissociation limit. It's a similar picture for the OH radical. This time we're looking at PBE. And again, you can see that the dissociation limit for PBE is incorrect compared to the spin PBE and the couple cluster result. But again, our implicit PBE is actually tending to the correct limit. It doesn't look quite as close here, but if you extend the axes out, it does actually tend to the correct limit. And again, we see this, it's not quite a kink this time, it's a little softer, but we see this kind of deviation from the spin PBA curve before we actually kink down towards the asymptotic behavior. And again, this corresponds to the implicit doublet energy becoming higher than the quadruplet state. Again, this does not occur for regular PBE. This only occurs when you actually use this implicit PBE result. So we're not suggesting that this implicit method is used for accurate dissociation curves. Clearly, in its current form, there are issues here. However, what we are showing here is a demonstration of, by removing this incorrect exchange interaction, you can actually bypass this dissociation error that you would get for a regular local or semi-local functional. So that brings us on to a more complicated functional. So can we actually extend beyond local and semi-local approximations and develop an implicit exact exchange, for example? The answer is yes, we can. And a similar approach, we can simply construct the right-hand side function B of R as the sum over the two exact exchange spin systems. On the left-hand side, the total response function is similar as before, it's just the sum over the two spin channels. So we can look at then the convergence of the implicit exact exchange results for three systems as well. And you can see here we've got the neon atom, which is a singlet state, kind of like a reference for a closed shell state system. We've got the fluorine atom, which is a doublet state, and we've got a triplet A2 diatomic again. What's clear this time is that actually double zeta is not enough. We do need to actually jump to a higher orbital basis set for the same auxiliary set. And this is likely due to the non-locality, the non-local behavior of the right-hand side function B of R being more difficult to represent. So this OEP, an implicit form, can be applied in a number of different ways. And one of the interesting applications that I've started looking at now is the extension to ensemble systems. So in particular, the ensembles of varying electron numbers. So if we imagine an ensemble of n electrons and with a system of n+1 electrons, we can write the total ensemble energy in the following form, where each of these subsystem energies can be expressed as follows. So same logic as we use to construct the implicit OEP equation. We can also construct an ensemble OEP equation and search for results for the local ensemble potential that best represents the ensemble of n and n+1. What's different here this time is that the response function on the left-hand side is actually the total ensemble response function this time. So it's the weighted sum of the two individual subsystems response functions. And again, you see the same on the right-hand side, where the right-hand side vector, B of R, is given as the weighted sum of the individual subsystem pieces. So in order to actually solve this equation, all we need is the exchange correlation potentials of both the n electron system and the n+1 electron system. Important thing to note here is if we're dealing with something which has n and then n+1 electrons, one of those two systems is going to have an odd number of electrons. So the work that has been done prior to this, talking about the implicit OEP, applies here, as each of these response functions can be broken down into their individual spin channels, one of which will be obviously an open shell system. So why might we want to actually investigate the derivative, the ensemble OEP? Well, one potential application is to try and extract a derivative discontinuity for local and semi-local functionals, which traditionally yield a zero derivative discontinuity. So for those who aren't familiar, the derivative discontinuity is a jump that occurs in the energy as a system crosses an integer number of electrons, as kind of illustrated by the figure on the right-hand side. As I said, the common semi-local or local approximations yield a very convex curve that doesn't actually have a derivative discontinuity. This error is largely due to self-interaction errors and is commonly known as the delocalization error. Hartree-Fock, or something like any non-local functional really, will yield the opposite. And it actually will yield a derivative discontinuity, unlike the local semi-local approximations. So mathematically, the derivative discontinuity can be calculated by taking the limit as omega goes to 0 of the potential for an ensemble where we add a tiny bit of an electron, and subtracting the potential where we subtract a tiny bit of an electron. And that's something that we started looking at now. We've got this ensemble equation implemented. So here is a quick example of the sort of thing that we can actually extract using this ensemble OEP. So here we're looking at the lithium atom, for example, and we're looking at ensembles of lithium with the cation and the atom, and lithium with the anion and the atom. And we're adding small amounts of electrons and removing small amounts of electrons. So you can see that as omega tends to 0, as I add a smaller amount of an electron and remove a smaller amount of electron, we actually tend to a constant within the vicinity of the atom. So up till around about 9 Bohr, we see a constant in the vicinity of the lithium atom. And then we get the sharp sort of decaying tail further out. So we haven't investigated too much the experimental comparisons here, so we haven't really taken the values and compared to experimental fundamental gap values. But this is something that we're going to be investigating thoroughly shortly, and there's going to be a paper coming out hopefully soon on that. So in conclusion then, what I've shown today is that we can reliably solve and efficiently solve the OEP equation within finite basis sets without incurring too much additional computational cost. We can construct implicit density functionals for open shell systems and achieve near spin DFT accuracy. And we can also extend this OEP framework in a variety of different directions. And today I showed you an example for ensembles of varying electrons in order to obtain the derivative discontinuity. I'd like to thank Tim, Nikitas, who worked very closely with me on this project, and also Tom, I think, is in the audience today, for his work on implementing the constraints, in particular on the screen density, and his work on the OEP equation, and also Nektaris for providing the initial code and for answering a lot of questions that we've had along the way. So thank you for listening, and I welcome any questions.